Another property of the normal distribution is, in fact, that it's preserved under linear combinations. Namely, that if I have a random variable, so the collection of xi are random variables. They're all random variables, but they're normal random variables. And notationally, we would say that each xi is normal, and it has a mean of mu I and a variance of sigma I squared. They're not independent normal. They're just simply normal random variables, and they, in fact, do have, in this formula, possibly a correlation between them. So now, again, this formula is telling us a couple of things. The first thing it's telling us is something about the moments of this linear combination. It's saying that the mean of this linear combination is given by the same linear combination of the means, and the variance of that linear combination of random variables is given by this double summation. So it's making a statement about moments, which should be familiar to you from probability theory. The second thing it's saying is that, in fact, this sum of random variables is normally distributed. Again, they're two very different things. That the property of the moments would be true for any random variables x. Has nothing to do with normality. That if the x's have any distributions with the given means and variances, this linear combination of x's has this given combination mean and this given combination variance. That's just statistics, and it's going to use the same derivation we'll see in just a minute. The key of this statement is that, in fact, we know more than the mean and the variance of this linear combination. We know its probability density function. And, in fact, that probability density function is, again, the normal. So in order to verify normality is, again, a moment-generating function argument. But, in fact, to derive it is going to take us a bit far afield. And what I mean by that is we need to know the probability distribution function of a normal vector, the vector of values x1 through xn. And that requires a certain amount of matrix algebra, and it's outside the scope of our work, so we won't do it. But I just want to highlight that, in fact, the argument we gave earlier with moment-generating functions will work here, namely that we can write down the probability distribution function of a vector of normal variables. And with that, we can define a moment-generating function, and we can, through a moment-generating function argument, prove the normality of that linear combination. So we're not going to do that because it's outside our scope significantly. But we can just quickly look at the moment calculations. The ones I made the point earlier have nothing to do with normality. So if I look at the expectation of this linear combination, well, the expectation of a sum is the sum of the expectations, always. When I'm working with expectations, I can always factor out multiplicative constants, and one sees readily that this just becomes then the summation of wi mu I. Okay, very familiar calculation. If I want the variance of this sum, we know by definition what we have to do is take that sum and subtract its mean. So I'll write that this way. I'll just do one algebraic step. Take the random variable and subtract its mean. Then I need to square it and take the expectation. That's the definition of variance. Take the random variable, subtract the mean, square it, do an expectation. So all I really need the trick of this calculation, of course, is to know what do I get when I square a linear combination of terms. And what you get, and we'll forget about the e for a moment, you get a double summation. You get a summation of wi, wj, and then you're going to get an xi minus mu I term and an xj minus mu j term. And both the i's and the j's are going to run through all the parameters from 1 to n. And this is easy to see if you just do a simple example. If you have an ax plus by and you square it, you see that what's happening is that you get 4 terms in the sum. Namely, you get an ax squared, a by squared, and then you get 2 terms with the mix. You get an ax times by and a by times ax. And that's how this summation is written. It's written allowing terms to be counted in that way that we just saw. Namely, I have a term in here, for example, where I is 1 and j is 2. And I have another term in that summation, for example, where I is 2 and j is 1. Well, they're the same term, but they're both counted rather than to try to simplify. So once I do that, now the expectation of a sum is the sum of the expectations, and we finally we have a double sum. And the wi's come out because they're multiplicative constants, and I end up with the expectation of this product term. And the author conveniently uses one notation, and this is common, that this term he expresses as sigma ij, noting that when I and j differ, that's a standard covariance, and when I and j are the same, it is, in fact, just a variance. And so sometimes you'll find this summation written this way, and I'll just recall it in case this is the way you're most familiar. You might find it written as the summation of wi squared sigma I squared. So all the pure variance terms. And then because each covariance term is counted twice, it's common that you see a formula that has a 2. And then this double sum it's a summation of all I strictly less than j, wi, wj, sigma I, j. So what we're doing is, instead of counting each mixed term twice in our double sum, we collapse it and put a multiplicative 2 in front. And this may be the way in which you've seen this formula expressed most often, and that's simply combining the ax by and the by ax into the same term. And that's what the 2 is doing. I being less than j means all combinations of I and j where I smaller than j, because all the combinations where I is equal to j are in the first sum, and all the combinations where I is bigger than j are counted in this same sub because of the 2.